Okay, so next, let's talk about some variants of this autoencoder model, right? So we have been talking about the autoencoder model already and also introduced the regularization terms for the model sparsity. Then we may consider, can we recognize this autoencoder model to help us? The main reason is because when we define the autoencoder models, normally we have to initialize all the dimensions for all the layers, right? So for the inputs, we know the input dimensions, then we have to design or decide the dimension for both the hidden layers as well as for the bottleneck layer, the embedding vector, right? As well as for the remaining layers. If we are using this like MLP as a model, then we can have to decide all the dimensions for the hidden layers, right, as shown here. Then you may wonder, how can we decide the dimension or dimension of this bottleneck layer, for the embedding vectors or the embedding targets, right? How large should be this bottleneck layer, the dimension? So, we can have different options, right? Normally, when we define this autoencoder model, we need to ensure we can learn very useful and meaningful embeddings, right, which can represent or carry the information from the inputs into a low-dimensional representation. Then, how can we guarantee this bottleneck embedding vector can carry the information about the inputs? If we have a bottleneck layer or the size is larger than the input size, then this model architecture will be meaningless, right? Because if this bottleneck layer, the size is even larger than the inputs, then we don't need to embed this input into this bottleneck layer, right? We can just use this input as embeddings, right, directly. Either we use much net space, and if we have a bottleneck layer, the size is much smaller than the input size, either we also lower down the model capacity because, for example, if we input a very large input into one single neuron, right, we assume this bottleneck layer has a very small dimension, like equals to 1. We use one single neuron to define this bottleneck layer. If so, then the model will be using this needs, right, because the capacity for the model to embedding the inputs into the embeddings will be so low, right? We just use one neuron to represent the embeddings, then it will be useless, right? Then the question comes, we normally have to decide the bottleneck layer, the size or the dimension very well. We need to balance between carry the information about the inputs and also need to ensure the capacity of the model as well. We need to balance between them, right? Then the question will be, how can we decide this bottleneck layer size? People have different ideas, right? Someone may say we can just design the bottleneck layer manually with different options and try them, right? However, this kind of way we have some weakness. The main reason is if we change the bottleneck layer, this dimension, then we are changing the model architecture. We have to rewrite the code, right? We have to rewrite the code for both the mapping from this hidden layer to this layer, right? And for the reconstruction as well. If we do minor changes here, then we need to change many other codes as well. It will be not a good idea. Then someone else proposed a new idea. Can we just set a bottleneck layer which is larger enough to carry meaningful information? However, we can control, the sparsity of it instead. Before, for example, if we have to set the bottleneck layer to be like 64 neurons, which will be optimal. If so, then we don't need to figure out this 64 manually, by different trials. What we can do actually is true. We can set the bottleneck layer with like 128 instead. However, we can control sparsity instead. In other words, we don't need to change the model architecture manually. Then we can control it by setting some of the parameters instead. So what does this mean? Actually, instead of tuning the bottleneck layer size manually, we actually can choose to tune the sparsity of the linear representation like H instead. So in this page, we show you the architecture for the sparse autoencoder. It will be very similar to the conventional autoencoder. However, the main difference lies in the learning function. If you still remember, for the conventional autoencoder, we define loss function as shown in this page, right? So we have this input to be x, and this fx will embed this into the embeddings, right, like h here. And this g will do the reconstruction from h to the output, right? We can minimize difference of this x versus this reconstruct output, right? And to define loss term. This is a conventional autoencoder model. Here we try to tune the dimension for the embedding vectors by adding one more term. The term is about regularization on this embedding representation we can get from this bottleneck layer. We add one more term as shown by the omega h as shown here, right? It defines the regularization term on the embedding sparsity. And we can use this L1 norm on this H vector to define the omega term on the regularizations. So it can yield a model which can learn useful features also without worrying about this bottleneck layer dimensions, right? So it will be a much easier way for tune the sparsity of the neural implementation without changing any code of this architecture, right? So this is one of the variant of the autoencoders we can try, to controlling sparsity of the embedded vectors by the bottleneck layer. It avoids us to tune the dimension for this layer manually, and instead we can just try to tune this recognition term instead. So we also have some other variants as well based on the autoencoder. In this page, we show two more. The first one is called autoencoder with this recognition term by derivative penalty. So the architecture of this variant will be very similar to the previous page, to this one. However, the main difference lies in the recognition term we define or we add into the object function. So this is not function, we don't need to say anything about this, right? Then the main difference will be about this regularized function. We define one more term added into the learning target. It's omega hx. And how do we define this omega hx? We define the omega hx this term to be the summation of all the internal hidden representations. And we sum these L2 norms of the partial derivative, and we sum these L2 norms together to define this omega term. And by adding this term, it will force the model to learn a function that doesn't change much as x changes slightly. We want to minimize this gradient, right? To ensure, this model will not change much if x changes. So this is another variant model we can try, based on autoencoders. And we also have another variant, it's called denoising autoencoder. Actually, we can do some minor changes to the autoencoder to use it to help us do the denoising of the inputs. What does this mean? So before we mentioned we define loss function to be this term, right? We do a reconstruction and minimize their difference. However, here if we are doing the denoising autoencoder, we assume that we have some noisy input. We want to ensure this autoencoder to help us remove the noisy information from the inputs and to recover a very clean output instead. So here let's assume we have the x tilde denoting these noisy inputs. And by the autoencoder, we can generate the output, right? And we want to ensure, given the noisy input, we can still construct a model or one autoencoder with encoder and decoder, which can obtain a precise and clean output by minimizing these outputs versus the clean ground truth. In this way, we can build an autoencoder, with some noisy training set, then further apply it to do the denoising of some other instances in the testing set. And what is this x tilde? So x tilde denoting some corrupted instances based on the feature inputs. And we can generate this x tilde by a corruption function, by adding some noise into it. What does this mean? In this page, we show you the architecture for the denoising autoencoder, and we try to utilize for the image denoising. And let's assume we have some noisy inputs denoted by the x tilde, right? And this image is so noisy. And we want to build an autoencoder with both the encoder and the decoder. Then we try to do the reconstruction to get the x prime, right, as you know on the right hand side. And this part is very similar to the conventional autoencoder with encoder, bottleneck, and decoder, right? Then, how can we guarantee this output will be as clean as possible? And we want to minimize the difference of this reconstruction output versus this clean ground truth without noise. We know this one was constructed from the noise input, and we want to minimize difference from the ground truth without the noises. In this way, we can build an autoencoder which can do the denoising. And we can train this model based on the training set. Given some data set that we do and based on the original data set, we can do the corruption and build such a model. And this model will be based on the noise input, and we can construct it to a clean input and to a clean output instead. When the model is built, we can further apply this model to a testing set, right, with noisy data there. And we can directly apply the model there. Given the noisy input, we can construct a clean output, right? So in this way, we can build a model for the image denoising to help us. And the main difference here is we will define the corruption function here to generate noisy data instances, and we also do some changes, to define loss function. Originally, we need to minimize the difference of this output versus the input, right? However, for the denoising task, we need to ensure the reconstruction output is as similar to the clean input as possible. So we make some changes to minimize the difference of this ground truth versus these reconstructions based on noise inputs, right? So you can see by doing some minor changes to the autoencoder model, we can apply the model to many of the tasks, and can also guarantee many of the properties of its outputs by the model. And you can also try this model by yourself, after class if you are interested in them, and you can also do some corruptions and also do the image denoising as well, right? Okay, so this is about the variance of the autoencoder. Next, we will move to the final part on the variation of autoencoder, which is very different from the above ones.